So today we will start from axiomatic definition of probability. Actually, you see the history of probability, this axiomatic definition comes after frequency definition. So there are some uh, limitations of the frequency definition. So that is why Kolmogorov is a famous mathematician. He is a Russian. In 1933, actually gave some sketch of this axiomatic definition. So this is now modern world, this is the modern definition of probability, and it is accepted throughout the world, throughout the globe. So what is the axiomatic definition? Let E be a random experiment and omega be the corresponding event space. Already we talked about this in the previous class. And also let F be the curly F be the class of subsets of omega forming the class of events of E. So already we discussed about the sigma algebra, that is the class of subsets of some set and class of events of E. A mapping P is from P from F to R, that is F is a class of subsets of omega and R is a real number. So its domain is the class of subsets of omega and codomain is the real number. So F is a mapping, is called a probability function. Is called a probability function defined on F, because your domain of definition is F and the unique real number PA determined by P is called the probability of the event A, where A belongs to, A is an event belongs to F, that is the class of subsets of omega. If the following axioms are satisfied, what are the axioms? Probability of A greater or equal to 0 for every event A belongs to the class of subsets of omega, that is F. P probability of certain event is 1, that is probability of omega is 1. And number 3, if A1, A2, AN etc. be countably infinite number of pairwise mutually exclusive events. Countably infinite number of pairwise mutually exclusive events. So what do you mean by pairwise mutually exclusive events? That means AI AJ, intersection of AI AJ is phi, right? AI AJ is phi, null set. So they are disjoint, mutually disjoint if I not equal to j, right? So this is the concept of pairwise mutually exclusive events, and obviously AI AJ belongs to this class of subsets F. So probability of A1 plus A2 etc. AN is equal to probability of A plus probability of A2 etc. probability of AN plus etc. So this is the three properties, three axioms. Probability of A greater or equal to 0, probability of certain event is 1, and if A1, A2, AN are countably infinite number of pairwise mutually exclusive events, then this relation holds. Okay, so these are the three axioms of probability according to the axiomatic definition of probability. Next we define probability. What is probability space? What is probability space actually? So this is a very good concept in probability. Our entire mathematical theory of probability will be built up by three objects. Only will built up by three objects. Actually 3 objects are required. The event space omega, just we talked about that. The class of events F, curly F, and the probability function P from F to R. Just like the we explained this in here, a mapping. Okay, these are the 3 objects and the ordered 3 tuple omega, curly F and P is called the probability space. So what is your probability space? Constitute the event space omega, class of events F, and the probability function P from F to R, where F is the class of events and its domain, and codomain is the real number. So P is the probability function. This constitute the probability space. So we may talk about some important deductions uh, using actually you have learned frequency definition, so you can use frequency definition to we can use frequency definition. I'm not talking about classical definition. Using classical definition you can easily verify this, because let me show you one example how to prove by using classical definition. From your classical definition you have probability of A equal to m by n, right? This is your using classical definition, and n is the total number of exhaustive, equally likely, mutually exclusive cases, and m is the number of cases favorable to A. Also you know that 0 less than equal to m less than equal to n. So from this, because n is a non-zero, so we can write m by n less than equal to 1. So m by n is nothing but your probability of A. So this proves that probability of A lies between 0 and 1. So this is a very simple proof by using classical. Now let me try to prove this by frequency definition. So what is your frequency definition? Earlier I explained that for frequency definition n of A is the absolute frequency. So your absolute frequency is less than equal to the total frequency n, okay, and n of A by n is the relative frequency, okay. So let us divide both sides, so you can write 0 to n of A, okay, by n less than equal to 1, and if you take the limit both sides, then this limit of this thing goes to probability of A, because this is your frequency definition. So if you take the limit n tends to infinity, if you take the limit n tends to infinity, capital N, obviously n goes to infinity, so this is nothing but your frequency definition. From the frequency definition it gives you the probability of A. So 0 less than equal to probability of A less than equal to 1. So this is the proof by using frequency definition. Now let us try to prove with the help of axioms. Let us try to prove this with the help of axioms. So using three definitions, okay. So by axiom 1, probability of A is greater or equal to 0, right? For every event A belongs to the you see belongs to the class of subsets of omega, that is F. So also probability of complementary event is also greater or equal to 0, we can say that, and we can write probability of complementary event equal to 1 minus probability of A. That we can also prove, because before we prove this we have to prove probability of A complement is 1 minus probability of A by using the axiomatic deduction. You can prove that, you can try that. So this is the result. So this is also greater or equal to 0. So from this we can say probability of A less than equal to 1, okay. So combining these two, we say that combining probability of A greater or equal to 0 and probability of A less than equal to 1, we can say that probability of A lies between 0 and 1. So this is the approach. In actually in axioms you have to use the axioms, and you have to write that you are using axiom 1, that is you are using the axiom, first axiom, because probability of A greater or equal to 0. Here also you are using probability of A complement greater or equal to 0. So this way you can prove probability of certain event is 1 by using the axioms, because using the axiomatic definition is very very important. And also probability of an impossible event is 0, that you can try to prove. It is very simple proof. And okay, this is the proof. This must be proved earlier, because with help of that proof we are using probability of A lies between 0 and 1. Now let us prove probability of A bar. Already we have used this identity, so let us prove that probability of A bar is 1 minus probability of A. And you see that you can write A union A complement is the event space, right, omega, and A intersection A complement is the phi, right? These are the two things with you. By axiom, using axiom 2, using axiom B in this case, using axiom B, we can say probability of omega is 1, right? So probability of omega is 1, and by axiom C, we can say, probability of omega is nothing but your probability of A union A complement. So using that is, we can say that probability of A plus A complement equal to probability of, because they are mutually exclusive, events, so probability of A complement. Okay, and probability of A complement, and this is 1, by axiom 1 this is 1, so this equal to 1. From this we can prove that probability of A complement is 1 minus probability. So these are the very simple proof. Okay, so you can use so many so many set relations you can prove by axioms, using the axioms. Okay, so let me now talk about deduction of classical definition from axiomatic definition. This is important question for university exams. So how will you deduce classical definition from axiomatic definition? So let us start. In this case, the event space omega is finite and contains n distinct elements. So we are assuming that the event space is finite and it contains n distinct elements, u1, e2, un. So omega is this one, and n distinct simple events are, suppose simple events are u1 equal to u1, u2, u2, these are our assumption, are equally likely, which means that the simple events have equal probability. Okay, so these are the events, these events are simple events and they are equally probable. So we can write probability of u1 equal to probability of u2, etc., equal to probability of un. Okay, also by axiom 2 already we proved, we have used in so many proof, that probability of omega, that is the event space, is certain event is 1, so that is equal to, your omega is actually this u1 plus u2 plus un, and these are all mutually exclusive since simple events are mutually exclusive. So we can write this relation to probability of u1 plus probability of u2, etc., probability of un. From 1 and 2 we can write this is equal to 1 by n. Look at that, using addendo, we are using addendo here, we can write 1 by n. So each of the events has the probability 1 by n. Probability of u1 equal to 1 by n, probability of u2 equal to 1 by n, probability of un is equal to 1 by n. Now let A be an event, any arbitrary event connected to the given random experiment. If the event A contains m distinct elements of omega, say u1i, ui1, ui2, uin, etc., where i1, i2, im take distinct values from the set 1 to n, from the set of natural numbers 1 to n, we can write A equal to this. We can write. So we can write probability of A equal to probability of ui1 equal to plus probability of ui2 plus etc., and finally we have probability of uin. Now look at that, already you have proved that all of them has the probability 1 by n. So 1 by n, 1 by n, and etc., 1 by n. So how many times you have 1 by n? M times, right? This should be im. There is a printing mistake. M times. Okay, so this is your m times. So naturally you have m by n. Okay, so this is a very simple proof. I think it is clear to all of you. So this is the result of a classical definition. So I have started from the axiomatic definition. So using the definition from using the axioms, that is the axiomatic definition, we have proved that classical definition. This is your classical definition. Okay. So next let us have some more on that. So addition rule, general addition rule is, if A and B be any two events connected to a random experiment, then probability of A plus B, sometimes we use the union symbol here, and here we can use the intersection. So it's a general addition rule. A plus B is probability of A plus probability of B minus probability of A intersection B. You can use the simple set inclusion principle. So let me show you in another way. So suppose you have the diagram, this is your A, this is your B, and let us write the regions as D1, D2, D3, and that outside is D4. So what are the notations now? So I am using D1 equal to, so let D1 equal to A intersection B, D2 equal to, what is your D2? D2 is A intersection B complement. Okay. What is your D3? D3 is A complement intersection B. And what is your D4? D4 is A complement intersection B complement. Okay. So this is the notation. Now all, you look at that, all DIs are mutually exclusive from the diagram. Yes. Okay. So their intersection will be phi. So all D1, D2, D3, D4 are pairwise mutually exclusive. So what is your LHS? LHS is P of A plus B, or you can write union here, no problem. So let me write your LHS. LHS is probability of A union B. So that is equal to probability of D1 union D2 union D3, and that is equal to probability of D1. You look at that, that's just these three regions and they are mutually exclusive. So we can write by axiom 3, using axiom 3, that probability of D1, probability of D2 plus probability of D3. Okay. And this is by axiom 3. Now what is your RHS? Your RHS is probability of A plus probability of B plus probability of B minus probability of A intersection B. Okay. So that is equal to, that is nothing but your, what is your probability of A? You look at that, your probability of A is D1 union D2. Okay. Again D1 D2 are mutually exclusive, so we can write probability of D1 plus D2. Okay. And what is your probability of B? Probability of, look at that in the diagram, probability of B is D1 union D3. Again D1 D3 are mutually exclusive, so we can write probability of D1 by axiom 3. I am using axiom 3, axiomatic approach actually. So D1 plus D3 and minus probability of A intersection B is your D1. Already we have assumed that. So finally if you write that, this one is cancelled from RHS, so you have the LHS equal to the RHS. So this is a very simple proof using this D1, D2, D3, D4, or you can use the simple set inclusion exclusion principles also. Similarly, for any three events ABC, we can prove that A union B union C is this is the result. Probability of A, you know that this is a set inclusion exclusion principle. So this is the thing. You can again draw the diagram. I'm not going into the detail of that proof, but let me show you the region. So this is your D1, D2, so there will be 8 regions, D3, this is your D4, D5, D6, D7 and D8. So all of you please try to solve this problem by using this diagram this way, or whatever you feel free to find out the solution in any way you can try. So these are the all about the applications of axioms and some rules, in general addition rule, and you can generalize the concept. So what is the theorem of total probability? That is, if a1, a2, an are n pairwise mutually exclusive events, so we can say this is the probability of a1 plus a2 plus etc. an equal to probability of a1 plus probability of a2 etc. probability of an. This is the theorem of total probability for n pairwise mutually exclusive events. Okay, so these are the important relations. Next we talk about two important inequalities, very important inequalities. One of them is the Boole's inequality, another one is the Bonferroni's inequality. So let us explain the Boole's inequality. It is very important. If a1, a2, an be n events connected to a random experiment E, then probability of a1 plus a2 etc. an less than equal to probability of a1 plus probability of a2 etc. probability of an. Okay, so let us prove that. Let us use mathematical induction. So let us prove for any two events a1 and a2. First let us prove for any two events a1 and a2. So we can say probability of a1 plus probability of probability of a1 plus a2 equal to, just we learned that for any two events a and b, we can write probability of a1 plus probability of a2 minus probability of a1 intersection a2, or you can say a1 a2. Simply you can use a plus, dot, or union, intersection, and this is equal to, this is obviously this is equal to probability of a1 plus probability of a2. Why? Because this thing is a positive quantity. By axiom 1 we can say that probability of a1 plus a1 a2 greater or equal to 0, right? If it is a greater or equal to 0 for any two events, so we can write by axiom 1 using the first axiom, we can say this, and if this is true then this is the relation. So for you see, the Boole's inequality is true for two events. The Boole's inequality is true for n equal to 2. Okay, for n equal to 2 it is true. Now we assume that the inequality is true for n equal to, it is true for n equal to m. Okay, where m is a positive integer greater or equal to 2, where m is greater or equal to 2, it's a positive integer greater or equal to 2. So we now consider m plus 1 events, right? Now we consider, n equal to m plus 1 events. As we know that from mathematical induction, if it is true for m plus 1 events, then it is true for any natural number, right? So events a1, a2, etc. a m plus 1, right? We are considering this m plus 1, and already we assume that it is true for n equal to m. Okay, so we can write probability of a1 plus probability of a2 etc. plus probability of am plus 1. Okay, am plus 1. Now this is equal to, already, okay, if it is true for n equal to m, we can write this relation. This is less than equal to probability of a1 by Boole's inequality a2 according to our assumption plus probability of AM. Okay, so this is the relation number 1, suppose. So now next, let me add a page here. So let us write probability of A1 plus A2 plus etc. AM plus 1, because I am considering AM plus 1 events, and that is equal to probability of A1 plus A2 etc. plus AM. So let us put a bracket here, plus AM plus 1. So what I am doing here, I am just separating these two. I am taking one parenthesis. Inside the one parenthesis I am writing A1 plus A2 plus AM, and another one is AM plus 1. So I am segregating this. So again you have, and this is equal to, for two events already we proved that if you consider this is one of the event and this is another, so already we proved that this is equal to probability of, this is true for two events, so we can write probability of A1 plus probability of A2 etc. plus probability of AM, okay, plus probability of AM plus 1, okay. Since it is, you have to write here, since it is true for n equal to 2 according to our assumption, right? And again you can use the equation 1, because this, actually this relation proves that probability of A1 A2 AM, this is AM, is less than equal to probability of A1 etc. AM. So you can write that thing here. If you write that, so let me write there. So if you write, then it will be probability of A1 plus probability of A2 etc. probability of AM using 1, okay, and probability of AM plus 1. So this is the proof. So hence it is proved that this inequality is true for n equal to m plus 1 whenever it is true for n equal to m. And so by mathematical induction, m is a mathematical induction, we can say that this is true for any natural number n, okay. So this is the Boole's inequality, okay. And m is a positive integer greater than 2, greater or equal to 2, okay. So this is a very important relation. This is called Boole's inequality. Now next we'll prove, or we'll show you just few steps on Bonferroni's inequality. This is also important. So look at that. If A1, A2, AN be any n events connected to a random experiment E, then probability of A1, A2, AN greater or equal to 1 minus summation I equal to 1 to n probability of AI bar, okay. So that we have to prove. Let me show you the number 1. So by Boole's inequality, we can write, just we learn that probability of A1 bar, if I apply, plus A2 bar, that is the complementary event, plus probability of AN bar less than equal to probability of A1 bar plus probability of A2 bar etc. probability of AN bar. Actually I am applying Boole's inequality, okay. So in the left hand side you can apply the De Morgan's law. What was your De Morgan's law? De Morgan's law is A1 plus A2 plus etc. AN whole bar, right? And that is equal to Okay, you can apply this. Sorry, there will be a product. I made a mistake here. Yeah, this is De Morgan's law. Actually, De Morgan's law is A1. What is your De Morgan's law? Probability of A1, probability of A union B whole bar is, don't write probability. Without writing probability, you write that A union B whole bar is A complement intersection B complement. So that I am writing here. So you have a plus and the whole thing will be a multiplication. Okay, and that is equal to probability of A1 bar plus probability of A2 bar plus etc. probability of An bar. So applying De Morgan's law, by De Morgan's law, and this complement complement of an event is, we can write 1 minus probability of A1 into A2 etc. into An, and that is less than equal to probability of A1 bar plus probability of A2 bar plus probability of An bar. Okay, and that is equal to, you see, if you change the sides, you will have probability of A1 A2 etc. An get are equal to, if you take it that side, 1 minus, this is the summation I equal to 1 to n probability of Ai bar. Okay, so that is your probability of Ai bar, just changing the sides. So this is your Bonferroni's inequality, the first one. Look at that, the result, we got this result. So similarly, you can prove the next one. I'm just giving it as a assignment. This number 2, you try to solve number 2 with the help of first one. So this is your Bonferroni's inequality. So these two inequalities, Boole's inequality and Bonferroni's inequalities, are very important. Lastly, I will talk about, I will give you another assignment. It's a theorem. It's a theorem that you have to prove if sequence An is, if sequence An is if sequence An be a monotone sequence of events, then you have a very important relation in probability of limit n tends to infinity An equal to limit n tends to infinity probability of An. Try this. This is your assignment. You should try this. This is very important relation. This is called continuity property of probability actually. So this is very, very important if it is a monotone sequence. So you have to prove, I'm just giving you a hint to prove. Case 1, you have to prove assuming it is monotonic increasing, and case 2 by monotonic decreasing, because it's a, we are talking about a monotone sequence, so it may be either increasing or decreasing. Okay, so this is our class today. So initially I talked about axiomatic definition. I have started from axiomatic definition of probability, the modern world accepting this definition, and this is the modern definition of probability. After that we talked about probability space. What is the probability space? We're talking about S delta sigma omega and class of subsets of S, that is F, and the probability function, and also some deductions using axiomatic definition, using frequency definition, also deduction of classical definition from axiomatic definition, and and we are talking about some general addition rule using some set inclusion exclusion principle, and also for three events, any three events ABC. And lastly, we write the theorem of total probability for n pairwise mutually exclusive events. And in the last section, we talk about two important inequalities, Boole's inequality and Bonferroni's inequality, and with the two assignment. Okay, so I'll stop here. We'll meet in the next class.